Close your eyes and imagine the space that lies beyond where we stand. In the earliest days of observation, the universe seemed complete. Early telescopes showed a stable arrangement of galaxies, moving only within predictable limits. This gave us the deep impression that nothing existed beyond the observable sky. For a long time, we simply believed that a single universe contained all the physical patterns of existence. However, this view gradually began to change. More precise instruments started recording small, yet consistent, irregularities in cosmic expansion. Different regions of the sky were expanding at slightly different rates, and these subtle variations assisted even as our tools became better and better. Such findings suggested that space might not follow just one uniform set of conditions after all. A major shift came from studying vacuum energy. This is the baseline energy that is present even in empty space. Quantum field theory describes how energy fields can settle into different possible states depending on the conditions of the early universe. A false vacuum is a state that appears stable, but it is not the lowest possible energy state. Under these early universe models, separate regions of space can settle into their own unique vacuum states. We can clarify this idea with a simple, everyday example. Think of water when it freezes. Many individual ice crystals form at once. Each crystal follows the exact same physical rules. Yet, each one grows in its own slightly different direction, based on tiny, local differences in temperature or pressure. In cosmology, the theory of inflation suggests that regions of space can separate in a similar way. One region might stop inflating and form a universe with specific properties, while another continues expanding and becomes a separate domain entirely. Studies of the cosmic microwave background strengthen this interpretation. This is the faint, ancient radiation left over from the very early universe. Improved measurements revealed subtle temperature variations. These variations are consistent with models where inflation produces many isolated regions. These regions become causally disconnected. This means no information can ever travel between them, because the space separating them expands faster than light itself can cross the gap. Imagine the observable universe as a single bubble. Inflation theory implies that many other bubbles may exist beyond our reach. The distance separating them grows as space expands. This is not because anything is blocking them. It is simply because the structure of space-time prevents any signal from crossing that immense gap. The possibility of separate domains emerged naturally from established physics, not from philosophical speculation. Evidence from quantum fields, cosmic expansion, and the structure of the early cosmos all began to support a broader view. The quiet realization that the universe may not be alone developed gradually. It came through refined instruments and deeper, more contemplative models of the early cosmos. As scientific tools advanced, the limits of what once seemed complete expanded as well. This progression has led to a calming thought that our observable universe might be only one region in a far larger and more expansive structure. Early models of the universe assumed that its structure was fully determined by the conditions right after the Big Bang. As measurements improved, scientists found limits that did not match this simple picture. Features of cosmic structure repeatedly fell within narrow ranges, suggesting deeper constraints behind the universe's behavior. Physicists began to focus on fundamental constants, such as the strength of gravity or the charge of the electron. These constants control how matter and energy behave, and they remain unchanged across all time and space. Their allowed ranges are extremely small. Slightly stronger gravity would cause stars to collapse, while weaker gravity would prevent them from igniting. Similar sensitivity appears across many constants, creating the impression of strict boundaries defining how the universe can function. A familiar comparison appears in engineering. A bridge can support weight only within a specific range. Too much or too little tension changes how the structure behaves. The universe operates in a comparable, narrow window between extremes. Inflation theory added context to these observations. Inflation describes the extremely rapid expansion of space shortly after the Big Bang. During this process, quantum fluctuations could cause different regions of space to develop slightly different properties. Under such models, these regions may end up with different fundamental constants or different outcomes in matter formation. Large-scale structures, such as galaxy clusters and cosmic filaments, reinforce this idea. Their patterns reflect exactly how matter responded to those early fluctuations. Simulations showed that even small changes in constants would prevent such structures from forming as we observe them. The close match between simulation and real data strengthened the view that these limits were not accidental. Star formation also revealed strict constraints. Stars require a precise balance between outward fusion pressure and inward gravity. If constants varied slightly, stable, long-lived stars would not form. Without these stars, the heavier elements necessary for planets and life would not exist in meaningful amounts. This created another clear example of narrow boundaries shaping cosmic behavior. These repeated observations led to interest in theories proposing multiple universes. If many universes exist with different constants, the fine-tuning of our own becomes one natural outcome. Only universes within certain narrow ranges can form stable structures, and our universe is one of them. Although this interpretation does not confirm the existence of other universes, it explains why so many physical limits appear tightly defined. The consistent pattern across cosmic expansion, galaxy formation, star evolution, and atomic behavior suggests a universe operating within a stable yet delicate balance. This balance is set by physical laws that allow only limited possibilities for existence. Early studies of Earth's history suggested that life emerged from a narrow combination of chemical and environmental factors. As scientific understanding expanded, researchers noticed that these conditions depended on physical rules set long before planets formed. This connection linked the existence of life to constraints in the early universe. The sensitivity of these conditions created the idea that biological rarity might reflect deeper structures of cosmology. Life requires stable atoms, long-lived stars, and planets capable of retaining complex chemistry. Each of these components depends on relationships between forces such as gravity, electromagnetism, and nuclear interactions. These forces are controlled by fundamental constants, and even small shifts in their values would prevent the formation of heavy elements like carbon or oxygen. Without such elements, biological molecules could not arise. This sensitivity suggested that life rests on a narrow foundation shaped by the earliest stages of cosmic evolution. Everyday experience offers a parallel. A seed can only grow if temperature, moisture, and soil composition fall within certain ranges. Too much or too little of any factor stops growth. Similarly, life depends on finely balanced planetary and stellar conditions. Earth's orbit, atmospheric composition, and long period of stability illustrate how rare such balance might be. The development of complex organisms added another layer of constraint. Multicellular life requires billions of years of stable energy from a star. If stars burned too quickly or too slowly, planetary environments would change too rapidly for complex structures to form. Observations of stellar populations showed that only a subset of stars maintain long-term stability. This further narrowed the window in which life could emerge. As scientists studied exoplanets, the scale of rarity became clearer. Many planets orbit in regions too hot or too cold. Others possess atmospheres dominated by gases hostile to chemistry required for life. While planetary diversity is vast, environments capable of sustaining liquid water and stable climates appear uncommon. Cosmology added another perspective. If inflation theory permits regions of space with different physical constants, then only a subset of universes would support structures compatible with life. In such a framework, the appearance of biological rarity becomes a statistical outcome. Our universe contains conditions that allow life because only such universes can develop observers capable of studying them. This perspective does not claim that life is unique to Earth. Instead, it describes how biological existence reflects a long chain of constraints that began in the earliest moments of cosmic expansion. The connection between life and cosmological parameters reveals how deeply living systems depend on the structure of the universe itself. Through these links, the emergence of life becomes a reflection of both local planetary factors and the large-scale rules that define the cosmos. Early surveys of the cosmos revealed large-scale structures that repeated across enormous distances. Galaxies formed in clusters, filaments, and sheets, creating patterns that appeared consistent, yet difficult to explain under simple models of cosmic evolution. These repeating arrangements suggested that matter might follow rules that arise from deeper physical processes, not from random distribution. As instruments improved, astronomers mapped the universe with greater accuracy. The structure known as the cosmic web became clearer. This web consists of long filaments of galaxies, surrounded by vast empty regions called voids. Such a pattern reflects the influence of tiny fluctuations present in the early universe. These fluctuations acted as seeds around which matter gradually accumulated. The repetition of these structures across billions of light years indicated that the underlying processes were highly regular. In everyday terms, similar patterns appear when grains of sand shift under wind or water. The grains follow simple rules, yet large dunes or ripples form repeatedly. The pattern results from small variations amplified over time. In the cosmos, gravity amplified early fluctuations in a comparable way, shaping the distribution of matter. Studies of the cosmic microwave background further supported this interpretation. The faint temperature variations in this radiation matched the patterns expected from early fluctuations. These variations were nearly identical across wide regions of the sky, suggesting that the universe's initial conditions were uniform but contained slight irregularities. Over billions of years, these irregularities produced the large structures observed today. However, theoretical models showed that such patterns could also arise in scenarios where multiple regions of space experience independent conditions. Inflation theory predicts that different parts of space may undergo expansion at slightly different rates. These differences could imprint unique patterns that repeat in ways not explained by a single uniform universe. Under these models, the repeating structures observed in our universe might represent only one possible outcome among many. Simulations of cosmic evolution helped clarify this concept. When researchers adjusted initial fluctuations or physical constants, entirely different cosmic webs formed. Some produced more clustering, others less. Some created rapid star formation, while others failed to form long-lived galaxies. The wide range of outcomes suggested that the patterns seen in our universe were specific to its initial conditions. This realization led to the idea that repeating cosmic patterns might reflect the broader structure of space itself. If many universes exist with different initial conditions, each would develop its own version of large-scale structure. The patterns in our universe would then represent one example within a larger set of possibilities. The consistency of these patterns across vast distances highlights how small differences in early conditions shape the universe's eventual form. While this interpretation does not prove the existence of other universes, it demonstrates how sensitive cosmic structure is to initial fluctuations. The repeated patterns observed across the sky reflect the combined influence of early quantum behavior, gravitational collapse, and the expansion of space. Through these processes, the universe reveals a structure that is both orderly and dependent on the smallest variations present at its beginning. Early attempts to describe the universe relied on models in which space behaved as a closed system. These models assumed that the laws of physics operated uniformly everywhere and that no external domain influenced cosmic evolution. As researchers developed more advanced theories of the early universe expansion, this assumption began to appear incomplete. Certain features of cosmic structure suggested that space might be capable of extending beyond its apparent boundaries, allowing possibilities to disperse in ways not visible within the observable region. The concept of a universe that can leak possibility arises from inflation theory. Inflation describes the extremely rapid expansion that occurred in the first fraction of a second after the Big Bang. During this phase, quantum fields experience fluctuations that influenced how different regions of space evolved. These fluctuations could cause regions to finish inflation at different times. When one region stops inflating, it becomes a pocket with stable physical laws. Other regions may continue expanding, forming new pockets with their own conditions. In this sense, the universe behaves like a landscape where new domains can branch off indefinitely. An everyday example offers a simple parallel. When boiling water cools, bubbles form at different points in the container. Each bubble expands independently, shaped by local variations in temperature or impurities. Although all bubbles share the same water, each forms a distinct pocket. In cosmology, Inflation predicts a similar process on a vastly larger scale, with pockets of space forming independently as the inflating background continues to expand. The idea that our universe might be one pocket among many gained support from mathematical models developed in the late 20th century. These models showed that inflation could continue indefinitely in some regions, a scenario known as eternal inflation. In this framework, no single universe describes all of reality. Instead, many regions form continuously, each with its own physical constants and structures. These regions cannot exchange information because the space separating them expands faster than light can travel. Observations of cosmic acceleration further supported this possibility. The discovery that the universe's expansion is speeding up implied the presence of dark energy, a form of energy that causes space to stretch. If dark energy behaves similarly to the energy that drove inflation, then pockets of space could still be forming far beyond the observable horizon. This would mean that the process shaping new regions of space has never fully stopped. Simulations of early universe physics demonstrated how small quantum variations could lead to large differences in the resulting domains. Some regions might form structures similar to those in our universe. Others might lack stable atoms or long-lived stars. The wide range of outcomes suggested that the space of possibilities is larger than any single universe can express. This perspective does not imply that our universe exchanges material or information with other regions. Instead, it indicates that the boundaries of our observable universe may not mark the limits of cosmic possibility. The physical laws we observe could represent one instance within a broader set of outcomes defined by inflation and quantum fluctuations. Through these developments, the idea of a universe designed to leak possibility became a natural extension of established physics. Rather than forming a closed and isolated system, the cosmos may consist of many regions shaped by varying initial conditions. The combination of inflation, dark energy, and quantum behavior offers a framework in which multiple domains arise continuously, each representing a distinct realization of the underlying physical landscape. Models of vacuum energy describe space as a field that can occupy multiple possible energy states. In quantum field theory, every region of space contains a baseline energy known as vacuum energy. This energy is not empty in the ordinary sense. Instead, it represents the lowest measurable activity of quantum fields. Under certain conditions, these fields can settle into different levels, forming a landscape of possible states rather than a single uniform configuration. A useful everyday comparison involves a surface with several shallow depressions. A ball placed on the surface can rest in any of these depressions. Each position is stable, yet the ball settles into a different spot depending on where it begins. In physics, these depressions correspond to vacuum states. Some states sit at lower energy levels than others. A state that appears stable but is not the lowest possible energy level is called a false vacuum. During the earliest stages of cosmic expansion, the behavior of vacuum energy played a significant role. Inflation theory describes a period when the universe expanded at an extremely rapid rate. This expansion was driven by a high-energy vacuum state. As inflation progressed, quantum fluctuations caused different regions of space to transition into different states. Some regions shifted into lower energy vacuum, ending inflation locally. Other regions remained in higher energy states and continued expanding. This process created a patchwork of domains, each shaped by the vacuum state it settled into. The energy level of a region influenced the strength of its forces, the behavior of its particles, and the evolution of its cosmic structure. Under this framework, the vacuum acts not as an empty backdrop, but as a physical component that determines the properties of the universe. Studies of particle physics provided additional support. Experiments involving the Higgs field showed that fields can adopt different stable values. The Higgs field gives particles mass, and its value determines how strongly different particles interact. A slight change in this value would alter the structure of atoms or prevent certain elements from forming. The sensitivity of these interactions indicated that the vacuum state directly shapes the material content of a universe. Large-scale observations also reflected the influence of vacuum energy. The accelerating expansion of the universe, attributed to dark energy, suggests that space contains energy that affects its growth. Dark energy behaves similarly to certain vacuum states, contributing pressure that causes space to stretch. This connection provided a potential link between early universe inflation and present-day expansion. Simulations of early cosmic evolution helped clarify how different vacuum states could lead to distinct outcomes. A region that transitions into a low-energy vacuum supports slow expansion, allowing matter to condense and form galaxies. A region that remains in a higher energy state expands too quickly for matter to accumulate. As a result, the vacuum landscape determines whether a region develops stars, planets, or long-lived structures. Under these models, the vacuum is not a single uniform state, but a dynamic landscape with multiple possibilities. Each possibility leads to different physical conditions. A universe is defined by the vacuum state it inherits, and variations in that state produce different cosmic outcomes. Through this framework, the structure of space becomes a central factor in shaping both the large-scale evolution of the cosmos and the smaller-scale behavior of matter. The formation of bubble-like regions in space emerges from models of cosmological inflation. Inflation describes a phase of extremely rapid expansion that occurred in the early universe. During this expansion, quantum fluctuations influenced how different areas of space evolved. Because these fluctuations were not uniform, some regions completed inflation earlier than others. When a region stopped inflating, it became a stable pocket of space with its own physical conditions. Regions that continued inflating stretched farther and eventually formed separate pockets. This sequence created a structure often described as a collection of bubble universes. A simple everyday example helps illustrate the concept. When water begins to boil, bubbles form at various points on the surface. Each bubble grows independently as steam pushes the surrounding water aside. Although all bubbles originate from the same water, each expands in its own direction and remains separated by thin boundaries. In cosmology, the inflationary background acts like the water, and the individual bubbles represent regions of space that have exited inflation. The boundaries between these regions arise naturally from differences in energy states. A region that leaves inflation enters a stable configuration, while the surrounding area may still carry higher energy. The expansion of the surrounding region prevents interaction between the two. As a result, each bubble becomes isolated. No information can travel from one bubble to another because the space separating them expands faster than light can cross. Mathematical models of inflation show that this process can occur repeatedly. New bubbles can form as long as the inflating background continues to expand. This scenario is known as eternal inflation. In this framework, the large-scale structure of reality consists of an ever-growing set of disconnected regions. Each region contains its own distribution of matter, physical constants, and possible cosmic histories. Simulations of inflation clarify how bubble formation depends on minute quantum fluctuations. A slight shift in a field's value can determine whether a region exits inflation early or remains in rapid expansion. These differences may be extremely small at the quantum level, yet lead to massive variations in cosmic outcomes. Some bubbles might form stars and galaxies. Others might remain empty or contain conditions incompatible with complex structures. Observational evidence does not allow direct detection of other bubbles, but certain features in cosmic data align with the underlying theory. The uniformity of the cosmic microwave background suggests that our own region exited inflation in a stable and coherent way. The slight temperature variations observed across the sky match predictions of early quantum fluctuations. These fluctuations are the same processes that, in theoretical models, would also generate bubble-like evisions in a larger, inflating space. The bubble universe concept offers an explanation for why the observable universe appears consistent in its physical laws, yet highly sensitive to initial conditions. Each bubble inherits its properties from the moment it exits inflation. Small differences during that transition produce different outcomes across bubble regions. Under this model, the universe we observe is one of many regions formed through repeated inflationary transitions, each shaped by quantum variations in the earliest moments of cosmic expansion. Quantum mechanics describes systems not as single definite states, but as collections of possibilities. Each possibility is represented by a mathematical object called a wave function. When a system evolves, its wave function can separate into independent parts that no longer influence one another. This separation is known as quantum branching. Under certain interpretations of quantum mechanics, each branch represents a distinct outcome that evolves separately from the others, forming a structure often described as multiple parallel realities. A simple everyday example appears in the behavior of light passing through a partially reflective surface. Part of the beam reflects and part passes through. In classical physics, these paths are separate events. In quantum theory, both outcomes exist simultaneously in the wave function until interactions with the environment cause a branching. Each branch contains one outcome, and once separated, the branches do not interfere with one another. In cosmology, quantum branching plays a role during the earliest phases of the universe. Inflation magnified quantum fluctuations to cosmic scales. Tiny variations in energy fields grew into differences in the distribution of matter. These differences influenced galaxy formation, star formation, and the large-scale structure of the universe. The branching of these early fluctuations produced a wide range of possible cosmic evolutions. Only one set of outcomes appears in the observable universe, yet models describe many possible branches that evolve beyond our observational reach. The mechanism that separates these branches is known as decoherence. Decoherence occurs when a quantum system interacts with its environment. This interaction suppresses interference between different possibilities, causing each to evolve independently. In large systems such as planetary formation or stellar evolution, decoherence occurs almost instantly. As a result, each branch becomes effectively isolated. Simulations of cosmic evolution show how branching affects structure. A small shift in initial fluctuations can determine whether a region forms a dense galaxy cluster or remains sparsely populated. Branching at the quantum level leads to dramatically different outcomes at cosmic scales. These outcomes diverge so strongly over time that they represent separate histories. Quantum experiments on Earth support the mathematical framework behind branching. Interference patterns demonstrate that systems maintain multiple possibilities until decoherence occurs. Measurements on particles, photons, and superconducting devices reveal that branching emerges naturally from the equations governing quantum behavior. Although these experiments do not show alternate cosmic histories, they confirm the underlying mechanism. In the context of multiverse models, quantum branching offers one explanation for the existence of multiple realities. Each branch forms a self-contained sequence of events shaped by initial quantum choices. These sequences do not interact, merge, or cancel. The observable universe corresponds to one such branch, while others continue without influence from our own. This framework does not propose that branching is optional or rare. Instead, it describes a continuous process built into the structure of quantum theory. Every interaction produces new branches. Over cosmic time, these branches accumulate, forming a vast collection of possible histories. Under this model, the universe is not a single path, but a structure shaped by countless quantum divergences that occur at every scale. The cosmic horizon marks the boundary beyond which light has not had enough time to reach the observer since the beginning of cosmic expansion. This horizon does not represent a physical wall. Instead, it reflects a limit imposed by the finite speed of light and the continuous growth of space. Because the universe expands, distant regions move away faster than light can traverse the increasing space between them. As a result, certain areas remain permanently beyond observational reach. A simple comparison appears when standing on a shoreline during thick fog. The fog allows visibility only to a certain distance. Objects beyond that distance still exist, but the light they emit cannot reach the observer. In cosmology, the cosmic horizon functions similarly. The expansion of space stretches the distance so quickly that signals from beyond the horizon never arrive. Inflation theory intensifies this effect. During the early universe, inflation caused space to expand at an exponential rate. This rapid expansion separated regions that were once close enough to interact. Once separated, no signal could cross the growing distance between them. Inflated regions became isolated zones, each evolving independently. The cosmic horizon today is a remnant of this process, defining the maximum distance from which light has ever reached Earth. Measurements of the cosmic microwave background provide evidence for this boundary. This faint radiation originates from a time when the universe was much younger and denser. Its nearly uniform temperature reflects conditions within the observable region. However, the radiation provides no direct information about areas beyond the horizon. The uniformity suggests that the observable universe shared common conditions before inflation magnified small fluctuations into cosmic scale structures. The horizon expands over time, but not fast enough to reveal new regions. Space stretches faster than light can travel, increasing the separation between distant zones. This means that galaxies currently near the edge of the observable universe will eventually move beyond the horizon. Their light will no longer reach Earth, even though the galaxies themselves continue to exist. Simulations of cosmic expansion illustrate how horizons arise naturally from the behavior of space-time. When expansion accelerates, as driven by dark energy, the horizon becomes more restrictive. The rate at which distant regions move away increases, reinforcing the separation. These simulations show that the horizon is not a fixed boundary, but a dynamic feature shaped by the evolution of the universe. In the context of multiverse models, the cosmic horizon plays a central role. If inflation generates many independent regions, each region becomes isolated by horizons. Observers within any one region can access only a small portion of the larger structure. The horizon therefore defines not only what can be seen, but also what can be influenced. Beyond it, other domains may exist with different histories, physical constants, or structures. Although the horizon prevents direct observation of regions outside the observable universe, it provides insight into the limits of cosmic knowledge. The mathematical structure of general relativity and inflation indicates that the horizon is a fundamental feature of expanding space. Through this framework, the observable universe is understood as one finite region within a much larger, potentially unbounded reality, shaped by the dynamics of space-time. Inflation theory describes a brief period in the early universe when space expanded exponentially. In many models, the field responsible for driving inflation does not stop everywhere at once. Instead, it decays unevenly across space. Some regions complete their transition quickly and begin forming matter, radiation, and structure. Other regions remain in a high-energy state and continue expanding at an accelerated rate. This process creates a patchwork in which inflation never fully ends on a global scale. A familiar comparison appears in the cooling of molten metal. When the material begins to solidify, crystals form at different points. Some areas harden early, while others remain fluid for longer periods. The entire material cools, yet no single moment marks the end of the process everywhere. In cosmology, inflation behaves in a similar way. Certain regions exit inflation and become stable universes, while surrounding areas continue stretching. The mechanism behind this persistence lies in quantum fluctuations. These fluctuations cause small variations in the energy density of the inflationary field. A slight increase in energy in one region allows inflation to continue longer. A slight decrease allows it to end. Even tiny differences can create enormous contrasts once expansion magnifies them. Regions where inflation persists grow faster than the regions where inflation has already ended, causing the inflating background to dominate the overall volume of space. This creates what physicists call a self-reproducing geometry. As long as some areas remain in the high-energy state, they continue generating new, expanding regions. Each region that exits inflation becomes a separate domain with stable physical laws. The surrounding inflating space continues to stretch and form additional pockets. This feedback structure results in a landscape of disconnected regions. Large-scale simulations model this behavior by tracking how fluctuations evolve. The simulations show that once inflation begins, it tends to persist in at least some regions indefinitely. These regions expand so rapidly that no signal can travel across the boundaries separating them. The geometry ensures that each pocket becomes isolated from the others. Observational data provides indirect support for this framework. Measurements of the cosmic microwave background reveal patterns consistent with inflation driven by a nearly uniform but slightly fluctuating field. The temperature variations reflect the same fluctuations that, in theoretical models, determine where inflation ends and where it continues. The consistency between data and models strengthens the view that inflation is sensitive to small variations in initial conditions. The accelerated expansion observed in the modern universe offers another parallel. Dark energy causes distant galaxies to move away at increasing speeds. While the mechanism behind dark energy differs from early universe inflation, both phenomena demonstrate that space can stretch at rates faster than signals can cross. This reinforces the idea that regions separated during inflation remain permanently disconnected. In the context of multiverse models, regions where inflation never fully stops represent the background in which new domains continually form. Each domain inherits its properties from the moment inflation ends locally. Slight differences in the inflationary field produce different cosmic outcomes. The overall structure becomes a continuously expanding environment filled with isolated regions shaped by early universe quantum behavior. Through this framework, inflation is understood not as a single event that concluded everywhere, but as an ongoing process that continues in distant, unreachable parts of space. The persistence of inflation allows for a wide variety of possible cosmic structures, with each region developing according to the conditions present when its expansion slowed and stabilized. Life on Earth relies on a narrow set of physical and environmental conditions shaped long before planets formed. Stable atoms, balanced forces, and long-lived stars created the background necessary for biological systems to appear. In multiverse models, these conditions represent one possibility among many, emphasizing how fragile the requirements for life are. Atoms depend on a precise balance between electromagnetic forces and particle properties. Small changes would prevent stable elements, such as carbon and oxygen, from forming, eliminating the building blocks of complex molecules. This sensitivity places life within a narrow range of physical rules. A familiar comparison appears in agriculture. A crop grows only when temperature, moisture, and soil fall within specific limits. Conditions outside those limits prevent development. Life shows the same dependence on finely tuned environments. Stars add another layer of constraint. Only certain stars maintain stable nuclear fusion for billions of years. Their long-term consistency provides planets with steady energy. Stars that burn too fast or too slowly fail to support environments where complex organisms can develop. Planets require additional factors: an atmosphere that retains heat, an orbit that allows liquid water, and geological activity that stabilizes climate. These features depend on heavy elements produced in earlier generations of stars. Their presence reflects a chain of events that is not guaranteed. Exoplanet studies revealed how uncommon Earth-like conditions may be. Many planets are too hot, too cold, or lack suitable atmospheres. Even planets within the habitable zone often show instability over long periods. Multiverse models treat this fragility as a statistical outcome. If many universes exist with different constants or starting conditions, only a subset would form long-lived stars and stable planets. Life emerges only where conditions allow it, and observers naturally appear in such regions. The link between life and cosmic parameters shows how deeply biological existence depends on early universe structure. Planetary environments alone do not determine habitability. Instead, life reflects precise and interconnected features of the cosmos, shaped by processes that began long before Earth existed. The limits of current physics become clear when examining phenomena that resist explanation within established theories. Quantum mechanics describes behavior at the smallest scales, while general relativity explains gravity and the structure of space-time. Both theories work with high accuracy in their respective domains, yet they cannot be combined into a single framework. This gap highlights missing elements in our understanding of the universe and shapes the search for models that might include multiple universes. One example involves the behavior of gravity at extremely small scales. General relativity predicts smooth curvature of space-time, while quantum mechanics predicts fluctuations in energy and position. When applied together, the equations fail to produce consistent results. This incompatibility suggests that a deeper theory, such as quantum gravity, is required. Multiverse models sometimes arise from attempts to build this deeper framework. Dark matter and dark energy provide another example of missing explanations. Observations of galaxy rotation and cosmic expansion show that most of the universe consists of substances that do not interact with light. Their properties remain unknown, and their existence is inferred only through gravitational effects. These unknown components indicate that the current model of matter is incomplete. In daily experience, missing pieces appear in simpler ways. When a machine fails, its behavior might seem unpredictable until a hidden component is discovered. Once that component is understood, the system becomes easier to describe. Physics faces a similar situation. Theories describe many observations but leave critical gaps unresolved. The early universe presents additional challenges. During the first fractions of a second after the Big Bang, densities and temperatures were so high that known physics cannot be applied directly. Models of inflation successfully describe rapid expansion, yet the precise mechanism that triggered inflation remains uncertain. The transition from quantum fluctuations to large-scale structure is understood in broad terms, but the details remain incomplete. String theory attempts to unify all forces, proposing that particles arise from tiny vibrating strings. The theory allows many possible configurations, each with different physical constants. This flexibility produces a landscape of potential universes, any of which could emerge depending on initial conditions. Although unproven, the theory illustrates how attempts to fill gaps in physics can naturally lead to multiverse ideas. Measurements of the cosmic microwave background reveal patterns consistent with early quantum behavior. Yet the data cannot rule out many competing theories. Some features, such as slight anomalies in temperature distribution, remain unexplained. These anomalies do not contradict known physics, but hint at influences beyond the simplest models. Efforts to detect new particles or forces continue in particle accelerators. Experiments have confirmed aspects of the standard model, but have not yet revealed the deeper structure that many theories predict. The absence of these discoveries suggests that important aspects of physics remain inaccessible at current energy scales. The limits of our theories create space for models that include multiple universes with different conditions. These models do not replace established physics. Instead, they extend it by addressing areas where current theories fail. Through this perspective, the gaps in physics highlight not only what is unknown, but also what might lie beyond the observable universe. Life depends on a sequence of events shaped by probability. When examining the conditions necessary for biological systems, researchers found that many of these conditions arise from rare combinations rather than common outcomes. This perspective led to the idea that the rarity of life on Earth reflects a much larger set of possibilities, most of which do not support living structures. In multiverse models, this rarity becomes one expression of the universe's sensitivity to initial conditions. The formation of essential elements, such as carbon and oxygen, requires specific reactions inside stars. These reactions depend on narrow energy levels within atomic nuclei. If those energy levels differed even slightly, the production of heavy elements would be greatly reduced. Without these elements, complex molecules would not assemble. The improbable alignment of nuclear properties highlights how chance shapes the availability of the materials needed for life. Planet formation introduces additional layers of rarity. A stable planetary system requires long-term gravitational balance. Many planetary systems observed through exoplanet surveys show chaotic or unstable arrangements. Some contain gas giants that migrate inward, disrupting smaller rocky planets. Others lack the heavy elements needed to form solid surfaces. Earth's formation required an uncommon sequence of collisions, accretion events, and orbital adjustments. In everyday terms, a similar idea appears in the formation of crystals. A crystal grows only when temperature, motion, and impurities align in precise ways. Small variations lead to different shapes or prevent formation altogether. Life follows a comparable pattern, emerging only when numerous conditions fall within a narrow range. The development of complex organisms also depends on long periods of environmental stability. Earth maintained liquid water for billions of years. Geological processes recycled nutrients, stabilized climate, and protected the atmosphere. These conditions are not guaranteed even on planets within habitable zones. Many planets experience rapid climate changes, atmospheric loss, or intense radiation from their stars. Statistical models of habitability show that the probability of life-supporting environments decreases sharply as more requirements are added. The presence of water alone is common, but the combination of water, stable climates, long-lived stars, and heavy elements becomes increasingly rare. This pattern suggests that life on Earth represents a narrow selection from a wide set of cosmic possibilities. Multiverse theories interpret this rarity as a consequence of variation across different universes. If physical constants initial conditions or cosmic histories differ across domains. Most universes would not support long-term chemistry or stable structures. Observers would arise only in the few universes where conditions allow it. Under this framework, biological rarity becomes a natural outcome rather than an anomaly. This perspective does not diminish the significance of life. Instead, it reveals how deeply life depends on a chain of improbable events and finely balanced conditions. The emergence of biological systems becomes a reflection of both the specific history of Earth and the broader landscape of possibilities suggested by cosmological models. Ancient cultures developed stories to explain natural patterns long before scientific methods existed. Many of these stories describe layered worlds, parallel realms, or repeated cycles of creation. Although these narratives were symbolic, their structure reflects patterns that appear in model cosmological theories. The recurrence of such themes suggests that human interpretation of the universe often gravitates toward ideas resembling multiple worlds. Myths from various regions describe realities that exist alongside the familiar one. Some traditions speak of upper and lower realms connected by specific pathways. Others describe cycles in which worlds are created, destroyed, and rebuilt. These stories reflect attempts to understand natural rhythms, such as seasons, climate, and geological change. They also reveal how people historically perceived the universe as larger and more complex than immediate observation suggested. A familiar everyday pattern appears in storytelling. When people encounter repeated events, they often imagine additional layers that explain those repetitions. In the same way, early observers use narrative structures to interpret cosmic patterns that lack direct explanation. These stories served as early frameworks for organizing observations. Modern science approaches the universe differently, but arrives at some structurally similar conclusions. Inflation theory describes separate regions forming independently. Quantum mechanics allows outcomes to branch into distinct histories. String theory proposes many possible configurations of physical laws. These ideas differ fundamentally from mythology in method and evidence. Yet they share the concept of multiple domains coexisting beyond ordinary experience. Comparative studies of mythology reveal recurring motifs. Stories of mirrored worlds appear in East Asian traditions. Cyclical creation myths appear in Mesoamerican cultures. Norse legends refer to interconnected realms separated by boundaries. Although these narratives were not scientific, they demonstrate a long-standing human intuition that reality might contain unseen layers. Scientific advances changed the basis for interpreting such ideas. Observations of cosmic microwave background patterns, the behavior of quantum fields, and simulations of early universe structure provide evidence for processes that can generate independent regions of space. These processes do not validate mythological stories, but show that the concept of multiple domains arises naturally in scientific context as well. The similarity between mythic structure and scientific models reflects shared attempts to understand complexity. Humans create narratives to explain patterns when direct information is limited. Science refines these explanations through measurement and theory, replacing symbolic stories with quantitative models. In the context of multiverse discussions, cultural myths provide insight into how humans historically conceptualized hidden layers of reality. Modern physics offers a different set of tools, but both approaches grapple with the same challenge: making sense of structures that extend beyond immediate perception. Through this connection, ancient stories become part of a broader effort to interpret the universe's depth and variability. Observers experience only one sequence of events, even though physical theories allow many possible outcomes. This limitation arises from the structure of measurement, the behavior of quantum systems, and the boundaries of the observable universe. The result is a situation in which humans perceive a single branch of reality, while other possible branches evolve independently. Understanding this limitation helps clarify why the universe appears consistent despite the range of possibilities suggested by modern physics. Quantum mechanics provides the foundation for this perspective. A quantum system can exist in multiple possible states, described by a wave function. When the system interacts with its environment, decoherence separates these possibilities into branches that evolve without influencing one another. Each branch contains a distinct outcome, but only one becomes part of an observer's experience. This process creates a structure in which many outcomes exist, yet any individual observer encounters only one. An everyday comparison appears in the branching paths of a large river. From a distant view, the river divides into multiple channels. Each channel carries water independently. A person standing on one bank, however, experiences only the specific channel in front of them. The existence of other channels does not change their immediate environment. Quantum branching functions in a similar way. Many outcomes exist, but the observer occupies only one. In cosmology, this limitation becomes more pronounced. The cosmic horizon prevents information from distant regions from reaching Earth. Even if other domains exist with different histories or physical laws, observers cannot detect them because space expands faster than signals can cross the separating distance. This boundary ensures that only the local region influences observable events. The structure of space-time reinforces this isolation. As galaxies move apart due to cosmic expansion, regions that were once connected become permanently separated. Their future evolution diverges, but observers in one region cannot track the changes in another. The observable universe therefore represents a small portion of a much larger structure. Simulations of early universe evolution show how small quantum fluctuations lead to distinct outcomes. A slight difference in energy density can influence whether a region forms dense galaxy clusters or remains sparsely populated. These differences accumulate over time, producing separate histories. Observers in one region experience only the outcome that develops locally. This limitation also appears in particle experiments. Measurements reveal one result, even though the underlying equations allow multiple possibilities. The act of measurement confines the observer to a single branch. Other branches continue mathematically but do not affect the observer's experience. Multiverse models incorporate these limitations by describing observers as confined to specific histories. Whether the multiverse arises from inflation, quantum branching, or variations in physical constants, the common feature is that observers perceive only one version of events. This confinement is not due to a barrier or a choice, but to the structure of physical processes that separate different outcomes. Through this perspective, the consistency of observed reality becomes a natural consequence of limited access. The universe may contain many possibilities, but each observer experiences only one thread shaped by local conditions, decoherence, and the boundaries of space-time. This framework explains why reality appears singular, even if many versions exist in the larger cosmological landscape. Future developments in physics aim to connect theories that currently operate separately. Quantum mechanics describes the smallest scales with high precision, while general relativity explains gravity and the behavior of space-time. Their incompatibility suggests that a deeper framework remains undiscovered. The search for this unified structure may reveal whether other universes exist and how they relate to our own. Efforts to develop quantum gravity reflect this pursuit. Quantum gravity seeks to describe gravity using the same principles that govern particles and fields. Several approaches attempt to achieve this, including string theory, loop quantum gravity, and causal set theory. Each offers a different perspective on how space-time might behave at extremely small scales. These models often produce multiple possible configurations of physical laws, implying that our universe may represent a single example from a broader set. String theory introduces the idea that particles arise from tiny vibrating strings. Different vibration patterns produce different particles. The theory allows many possible vacuum states, each with its own physical constants. This variety creates what researchers call a landscape of possible universes. Although unproven, the structure of the theory supports the concept of neighboring domains with different properties. Upcoming observations may provide clues. Advanced telescopes will measure cosmic microwave background patterns with greater accuracy, searching for signals that could indicate interactions beyond the observable universe. Precise measurements of polarization, temperature variations, or slight distortions may reveal traces of early universe processes that point to multiple regions of space. Particle accelerators offer another path. Experiments that probe high energies may uncover particles or interactions that extend the standard model. Discovering new fields or symmetries could clarify the conditions that determine physical constants. Such findings would influence theories that predict multiple universes with varying properties. Studies of dark energy and cosmic acceleration also play a role. Dark energy controls the expansion rate of the universe, and its nature remains unknown. If future observations reveal that dark energy changes over time or behaves differently than expected, it could indicate a deeper structure underlying cosmic expansion. This structure might include regions with different expansion histories. In everyday experience, technological progress provides a parallel. Devices that once revealed only surface-level behavior now expose fine details after improvements in resolution or sensitivity. As instruments advance, previously hidden features become observable. In physics, similar improvements may reveal aspects of the universe that were inaccessible before. Simulations will continue to shape understanding as well. As computing power increases, models of early universe physics will incorporate more variables. These simulations may show how small changes in initial conditions produce different outcomes, strengthening the view that multiple universes could arise naturally. The next generation of physics does not aim specifically to prove the existence of other universes. Instead, it seeks to resolve gaps in current theories. Whether through quantum gravity, improved observations, or new particles, advancements may reveal patterns that naturally extend beyond the boundaries of the observable universe. Through these developments, the search for neighboring universes becomes part of the broader effort to understand the fundamental structure of reality. The idea of mapping the universe suggests a goal of describing every region of space and understanding its structure. Advances in astronomy have expanded this map for centuries, from early star charts to modern surveys that reveal billions of galaxies. Yet the accelerating expansion of space imposes limits on this effort. No matter how advanced observational tools become, certain regions will remain permanently inaccessible. This ensures that a complete cosmic map can never be achieved. The expansion of the universe plays the central role in this limitation. As space stretches, distant galaxies move away from one another. Beyond a certain distance, this recession speed exceeds the speed at which light can travel across the expanding space. These regions move beyond the cosmic horizon. Their light will never reach Earth, making their contents unobservable. Even if technology improves indefinitely, no instrument can detect information that cannot physically arrive. A familiar everyday example appears when watching a landscape recede from a moving vehicle. As the vehicle accelerates, more distant features fade from view. No amount of visual enhancement can restore objects that have already passed beyond the visible range. In cosmology, the same principle applies, but the scale is far larger and dictated by the structure of space-time. This limitation becomes more significant as cosmic acceleration continues. Observations show that dark energy drives the expansion of the universe at an increasing rate. As a result, more galaxies drift beyond the horizon with time. The observable universe therefore represents a shrinking fraction of the total cosmos. Regions once visible will eventually move out of reach, even though they continue to exist. Simulations of cosmic evolution illustrate how boundaries emerge naturally. When expansion accelerates, the geometry of space-time forms zones that cannot influence one another. These zones evolve independently, producing separate histories. The map of one zone provides no information about the others. Each becomes a self-contained region, defined by its own observable structure. Efforts to measure the cosmic microwave background reveal the greatest extent of the observable universe. Yet, even this radiation originates from a specific moment in cosmic history. It offers no information about regions beyond the horizon or about areas shaped by different initial conditions. Its uniformity suggests that the early universe shared common features, but it cannot reveal the full scale of reality. In multiverse models, the impossibility of a complete map extends even further. If inflation produces many independent domains, each with distinct physical properties, these domains lie permanently beyond contact. No signal can traverse the expanding space that separates them. Even if their existence is implied by theory, their contents remain inaccessible. This framework redefines the concept of a cosmic map. Instead of a single, complete diagram of all space, the map becomes an evolving representation of the observable region. Its boundaries change over time, reflecting both the limitations of observation and the structure of space-time. The unreachable regions form part of the universe, yet they remain outside the scope of measurement. Through this perspective, the universe is understood as a structure too large to chart fully. The combination of cosmic acceleration, horizon boundaries, and inflation ensures that any map remains partial. This limitation does not hinder scientific progress. Rather, it clarifies the scale of the cosmos and the boundaries within which observation is possible. Parallel realities arise naturally in several theoretical frameworks, even though they cannot be detected directly. These realities describe sequences of events that diverge from one another due to differences in initial conditions, quantum fluctuations, or variations in physical constants. Each sequence forms an internally consistent history, yet observers confined to one cannot access the others. This structure creates a landscape in which multiple versions of cosmic evolution occur independently. Quantum mechanics provides one foundation for this idea. A quantum system follows a wave function that contains many possible outcomes. When the system interacts with its environment, decoherence causes these outcomes to separate into branches that evolve without interference. Each branch represents a distinct sequence of events. Observers experience only the branch aligned with their measurement outcome, while the other branches continue beyond perception. A familiar everyday comparison appears in the creation of multiple drafts of a document. Each draft contains different choices and developments, yet only one becomes the version an individual continues working on. The others remain separate, following their own trajectory. Parallel realities function in a similar manner. Many versions exist, but observers remain within one. Cosmological models add a larger scale perspective. Inflation theory describes regions of space exiting rapid expansion at different times, forming isolated domains. Each domain develops its own structures and physical laws. These regions cannot exchange information because the space between them expands faster than signals can travel. Each becomes a parallel reality shaped by its initial conditions. String theory also suggests the existence of multiple domains. The theory allows many possible vacuum states, each with unique physical constants. If different regions settle into different vacuum states, they form distinct universes. These universes coexist, but remain separated by energy barriers or expanding space. Simulations of early universe development show how small variations in initial conditions lead to dramatically different outcomes. A slight difference in density can influence whether a region forms large galaxy clusters or remains mostly empty. These divergences accumulate over billions of years, producing distinct histories. Each history represents a parallel reality that shares a common origin but evolves independently. Observational limits prevent direct detection of these parallel domains. The cosmic horizon blocks information from regions too distant to influence Earth. Even within quantum branching frameworks, the separation between branches prevents interaction. The lack of direct evidence does not contradict their existence. It reflects structural boundaries built into physical laws. In multiverse discussions, parallel realities represent a natural consequence of theoretical models, rather than a speculative extension. Whether arising from quantum branching, inflationary processes, or variations in physical constants, these realities remain hidden because of fundamental limits on communication and observation. Through this perspective, the universe becomes part of a larger structure containing many independent histories. Each history develops according to its own rules and initial conditions. Although observers cannot detect these parallel domains, their existence offers a framework for understanding how small variations in early processes can lead to a wide range of possible cosmic outcomes. The evolution of a universe depends on its initial conditions, physical laws, and long-term cosmic processes. Small variations in these factors lead to different large-scale outcomes. As a result, theoretical models describe a landscape in which universes may follow distinct trajectories toward their final states. Some universes expand forever, others collapse, and some enter periods of accelerated growth. Each trajectory represents a different cosmic ending shaped by its underlying structure. General relativity allows several possible futures. If the density of matter is high enough, gravity can slow expansion and eventually reverse it. This produces a collapse known as a big crunch. In scenarios with lower density, expansion continues indefinitely. The universe becomes colder as galaxies drift apart and stars exhaust their fuel. Dark energy introduces another possibility. If its influence strengthens over time, space may expand at an accelerating rate that eventually overcomes all forces, producing a state known as the Big Rip. A familiar everyday analogy appears in the behavior of a candle flame. A flame may burn steadily, fade gradually, or vanish suddenly, depending on airflow, fuel, and temperature. The underlying chemistry is the same, but small differences in conditions produce different outcomes. Cosmic evolution follows a comparable pattern. The same physical laws allow multiple futures depending on initial values and long-term energy balance. Inflation theory broadens these possibilities. In models where inflation continues in distant regions, each domain can settle into a vacuum state with its own constants. These constants determine how matter forms, how stars evolve, and how expansion proceeds. Some vacuum states allow long-lived stars that support stable structures. Others produce rapid expansion that prevents galaxies from forming. Each vacuum state shapes the universe's ultimate fate. Simulations of cosmic structure show how slight differences in early fluctuations lead to divergent outcomes. A region with higher density may form massive clusters that merge over billions of years. A region with lower density may evolve into a sparse environment dominated by empty space. These differences influence not only the development of galaxies, but also the long-term behavior of expansion and gravitational collapse. The discovery of dark energy added more variation to possible endings. Dark energy causes the current accelerated expansion of the universe. Its behavior over time remains uncertain. If dark energy remains constant, expansion continues indefinitely. If it weakens, gravitational attraction may eventually dominate. If it strengthens, the fabric of space could stretch faster than structures can remain bound, leading to a more extreme ending. In multiverse models, different universes follow different endings because their initial conditions, vacuum states, and energy distributions vary. Each universe evolves independently, shaped by its own parameters. Some may collapse early, some may expand without limit, and others may transition into states unlike anything observed. This framework positions the fate of our universe as one example within a larger set of possible trajectories. The ending we observe depends on the specific conditions present in our domain. Other universes shaped by different structures or constants, follow their own divergent paths. Through this perspective, cosmic endings become part of a broader landscape of possible outcomes defined by the fundamental rules of physics. Scientific theories describe how the universe evolves, how matter forms, and how cosmic structures emerge. Yet even as these explanations grow more detailed, they reveal questions that remain unresolved. These questions persist not because of missing data alone, but because the structure of the universe imposes fundamental limits on what can be known. In multiverse frameworks, these limits gain additional significance, suggesting that some aspects of reality may remain beyond reach, regardless of future progress. The observable universe represents only a portion of a much larger whole. The cosmic horizon prevents information from distant regions from reaching Earth. Even with perfect instruments, observers cannot access events beyond this boundary. This limitation ensures that questions about what lies outside the observable region remain open. Whether other domains exist, how they behave, and how many there may be, are questions shaped by the geometry of space-time rather than by measurement alone. A familiar everyday situation illustrates this principle. When viewing a landscape through a window, the frame defines the visible area. The scenery beyond the frame continues to exist, but its details remain unknown from that viewpoint. No improvement in clarity or brightness reveals what lies outside the frame. In cosmology, the observable universe functions in a similar way. The boundaries are determined not by equipment, but by the nature of space and time. Theoretical physics deepens this limitation. Quantum mechanics describes systems in terms of probabilities rather than certainties. Some aspects of quantum processes cannot be predicted with absolute precision, regardless of the quality of the measurement. These inherent uncertainties appear in every branch of physics and set limits on how fully any model can describe the universe. Efforts to unify gravity with quantum mechanics introduce additional unknowns. Competing theories provide different explanations for the structure of space-time at the smallest scales. Each theory describes a possible framework, yet experiments cannot currently distinguish between them. Without the ability to access energies far beyond those available on Earth, some details may remain unresolved indefinitely. Multiverse models extend these questions rather than remove them. If many universes exist with different physical constants or initial conditions, determining why our universe has its particular properties becomes more complex. Some models treat these properties as statistical outcomes, while others suggest deeper organizing principles. Yet no observation can directly access other universes, leaving these interpretations open. Simulations of cosmic evolution reveal how small differences in initial conditions lead to distinct outcomes. These differences accumulate over billions of years, producing a range of possible histories. Understanding why one particular history unfolded in our region may always involve an element of uncertainty. Even complete knowledge of present conditions cannot reconstruct all aspects of the initial state. In this context, the final unanswered question is not simply what lies beyond the observable universe, but whether complete understanding is possible at all. The limits imposed by horizons, quantum uncertainty, and theoretical ambiguity suggest that some aspects of reality may remain permanently out of reach. These limits do not reduce the value of scientific progress. Instead, they define the scale of inquiry and clarify which questions can be answered. Through this perspective, the pursuit of cosmology becomes a balance between expanding knowledge and recognizing fundamental boundaries. Even as theories describe the universe with increasing precision, the structure of reality ensures that some questions remain open, continuing to guide scientific exploration.